Myself, Muhammed Rashique, Assistant Professor in Physics, Vedavyasa Institute of Technology. My topic is the dual nature of light. Light as a wave, sometimes it behaves light as a particle. Some key points I'm discussing now here. Introduction, contribution of history, for that Newton corpuscular theory by Huygens. Then Young's experiment, diffraction of light, Compton effect, and finally conclusion. Introduction. The dual nature of light means light has a two different nature. Sometimes it behaves like a particle, sometimes it behaves like a wave. I discussed a few of the famous experiments which establishes the nature of light. Light is a wave or a particle. Contributions and history. Newton corpuscular theory. Newton's corpuscular theory based on the following points. First one, light consists of very tiny particles known as corpuscular. These corpusculars on emission from the source of light travel in a straight line with a high velocity. When these particles enter the eyes, they produce image of the object or sensation of vision. And finally, the corpuscles of different colors have different sizes. Huygens principles. The Dutch scientist Christian Huygens, a contemporary of Newton, proposed Huygens principle, a geometrical way of understanding the behavior of light waves. Huygens principle. Consider a wavefront of light. First one, each point on the wavefront is a new source of a spherical wavelet that spread out spherically at wave speed. And the second one, later time, the new wavefront is surface that is tangent to all of the wavelets. Young's experiment. The phenomenon of interference was first demonstrated by Thomas Young in 1801 with a simple experiment. This phenomenon requires for its explanation that light must have a wave nature. Diffraction of light. That is, Chin Fresnel used Huygens wave theory gave explanation of the phenomenon of diffraction of light, bending of light around the sharp obstacle. The effect is found to be significant when the dimension of a diffraction element becomes comparable with the wavelength of light. Planck's resolution. The Planck hypothesis that the black body radiation was produced by resonators. Resonators were submicroscopic charged oscillator. The oscillator could have discrete energy. En is equal to NHF is a very famous equation where N is called the quantum number, F is frequency of vibration, H Planck's constant. Key point is quantized energy state. Last, Compton scattering. The Compton assumed the photons acted like other particles in collisions. Energy and momentum were conserved. The shift in wavelength is delta lambda is equal to lambda minus lambda naught. That is equal to h by m naught c 1 minus cos theta. Conclusion. Finally, we concluded that the phenomenon of interference, diffraction, and polarization of light are well explained by considering a wave nature of light. On the other hand, the phenomena like photoelectric effect, Compton effect, Raman effect, etc., require practical nature of light. The both complementary principles stated that the wave and particle description are complementary ways. According to the uncertainty principle, it is impossible to design an experiment which will show both the particle and wave nature at the same time. Thank you.